Hello everyone, it's August 20th. Let's do this. Count submatrices with all ones. So yesterday was sub-square matrices. This is sub-matrices. So we're getting a little bit more difficult. Let me think about maybe we should do the same trick as what we did yesterday. Like DP. Ooh, I'm not sure about DP though. So yesterday's idea is we're ending at here, right? So we have ending at here, and then we know it's gonna be this, this, or this, right? So we can compute. Like if I need to find all the this might be different. This might be different. But I'm not sure. I mean, we can try DP first and see how it goes. So we need to find all the submatrices, right? So we say if I can find all the submatrices, let's say I want to find all the submatrices ending here. Okay, which is so at bottom right is this, and we have is 1, 2, 3, 4. So I have 4. Right? So 1, 2, 3, 4. I don't have another one. So I have some matrices here, but this one will also include things that does not belong here. So technically you cannot do it. This one the same, right? Technically you cannot just include them. So I guess it's out of the question. Maybe we can go back to the idea we had yesterday, which was not appropriate for a square matrix, but maybe it's appropriate for now. So we'll count. We'll count. Hold on, let me think. So basically, we want to find everything ending at here, right? So essentially, we want to know at this level, right? How many do we have? And then with 2, how many do we have? With 3, how many do we have? Right? So essentially, we do need to find ending at here, right? Ending at this. We're talking about this row. How many do we have? That depends on if we move to the left, what is the consecutive? What is the consecutive? What is the consecutive? Because if we do prefix, we'll get the count total, right? And then we'll get prefix count here as well. And not really the prefix count. And essentially we just repeat the same strategy, because now we just group these two together, right? We want to know how many. And now we group, we cannot group anymore. So like for this, I have myself, and then I have this. So we have 2, right? And if we look up, it's the same thing. We just need to know how much I can extend here. And I would pick the smaller of the 2. So that's what I need to do. We need to pick the smaller of the 2. But how do I know how much do we count? We will turn into 0 once we hit. We'll turn into 0. The same trick as we had yesterday, honestly. So in this case, will be 1, 0, 1, 1, 2, 0, 1, 2, 0. Okay, so for each one, I'll count. This is basically the consecutive. What's the consecutive? So this I have 1. This is nothing. This I have 1, right? This is 1, and then I look up. Ooh, look up. Maybe I don't need to look up. Can I do this as well? Like if it's a 0, which is 0, so let's say I'll add, so this will be 2. But 0 I don't add. So this will be 3. This will be 4. This is still 0. So basically here, what we say is, this I have 1. Going this way, I have... let me think. Let me think. Going up. Because I need to include the ones up. Right? So up I can have however many. Which is essentially ending at this one. How many? But it depends on, like, if horizontally I'm less than the one above me, then I actually cannot. The one above me, if it only computes this. So I do think we have to go up, which make this O(n) tripled. Ugh. Hold a sec. So this is going to be 1, 1, and 2, right? So another thing we need to do is we need to keep track of the smallest. The smallest. So like at each one, I know what's the maximum, right? So I look up. I need to know what's the maximum. What's that, right? And I take the minimum of the 2, and then I look up. Then I'll take the minimum of that. But I need to take the minimum of every single one of them. Oh, this is not looking good. Because every one I have to go up. But 150, 150, maybe O(n) triple, maybe it'll work. So yeah, so I have 1, 2, this one have myself, right? And then I look up, I pick the minimum of the 2 until I hit a 0. So this is actually another one. And here I have 2, and then a 0, so I just get 2. This one I get a 1. I go up, I get a 1. I go up, I get a 1. This is a 2. I go up because this is a 2, so I go up, I get another 2. So the total number is, ooh, wait, I got 2 here, this and this. All right, and I go here. I need to get this, so I have this and this. That's 2. How come I only have 12? Where did I count wrong? All right, let's do this. This is a 1, this is a 1, this is a 2, this is a 2 because it's only 2. This is a 3, and this is a 4. 1, 2, 3, 4. Yeah, that's 13. Zero, 1, 2, 0. 0, 1, 2, 3. 2, 3, 0. Okay. So now we need to count. So the first row is just going to be 1, 2. Second row here, I need to go up. So this is a 2. This one need to go up. This is a 4. This one just by itself because up is this. This is a 1. This one is 2, but up is only 1. So go up, I only take 1, and then go up, I only take 1. Right? So this is still adding them together. And this, yeah, because I'm a 3. This is smaller than me, so I take 2. So 2. So this is 7. So I added them together. 1, 2, 3, 4. That's a 10. 13. 17, 24. Yeah, but that's still an edge case because I could have a scenario like this. In fact, I think we should try this scenario. Right, I can have, let's say 1, 2, 3, 0. 1, 2, 3, 0. And 1, 2, 0, 0. Things like that. So in this case, it's not adding them together. Right? So this is a 1, 2, 3. Oh, this is a 1, 2, 3. This is a 2, 4, 6. This is a 0. This is 1. So this is actually 3. 1, 1, 1. This is a 6. So it's a 1, 2, 3, 4. That's 10. That's 18. 18 plus 9 is 27. We can actually try this. So just a little bit change, right? So we go 1, 1, 0. This one gets a 0, and then here we're gonna do this. Right now we return 27. Yep. You see, 27. So I guess I don't like it, but I think we have to go untripled. And we'll create this based on this, and then we don't have to create this. Okay. So we will create a prefix sum for each row, but reset once a 0 is encountered. This tells us the number of submatrices with height of 1 ending at each cell. When computing the result, we will go up, right, to find the max number of submatrices with height equal to 1 at each cell above us. We will take the min of them, right? We'll take the min of them to find, right? To find the number of submatrices with different heights. The runtime is slow at O and tripled. but I hope the solution will pass because the constraint has the size of the original matrix not exceeding 150. So there is a possibility that it's m equals mat.size, n equals mat0.size. Okay, for int I 0I smaller than I plus. So the first one we will let it go, right? Well, first one we'll let it go. The second one we will. Yeah, so basically if it's a 0, we skip. If it's not a 0, we'll add to the previous. Yeah. And the first one will always stay the same. So yeah. Say for int j equal to 1, j smaller than n, j plus plus, right? So we say if mat ij is not equal to 0, right? Then we say mat ij plus equal to mat ij minus 1. If it's a 0, we just skip it. If it's not a 0, we'll always add to the left. So this is the preparation. Then we set the rest equal to 0, and then we'll do the first row because it's just inevitable. Actually, no, we can actually just go through everybody. I equal to 0. Smaller than m plus plus for int j 0, j smaller than n, j plus plus, and do a k, right? So basically trying to add myself, okay? So it's a rest or plus equal to, oh, actually we can say, if it's 0, we can skip. So if mat ij 0, we'll continue. We skip the 0. Okay? If it's not 0, now say rest or plus equal to mat ij. Okay. Then for int k equal to I minus 1, k is large equal to 0, and mat kj is not equal to 0. K minus minus. Then we basically have to keep track of the smallest. So int min shall equal to min val mat ij. This is what we're starting with, right? So we update min val equal to std min val and mat kj. Okay, and then rest plus equal to min val. And then we go one up, try it, go one up, try it until we cannot try it anymore. Then we're done with the current one, and then we just move on. We get through everybody, and we'll return rest. I'm not sure if there is any. There probably is room for improvement, honestly. Okay. Right, let's hope that does not time out. It does not. It does not time out. In fact, it's ridiculously fast. Which just means that we hit the correct solution on the head. I'm pretty pleased with this result. Enumeration. Enumeration. Well, that's exactly how we're doing. Ooh, poo, poo. Ooh, ooh. I think that's exactly the same as what we do, but why do you call the solution? Enumerate each position. Yep, this is the key. Enumerate the height of the sub-rectangles and check how many of them are valid. Yep, that's exactly what we do. Wow, this is almost exactly the same. Oh, it's not ON tripled. It's yeah, OM squared. That's fine. Monotonic stack. Oh, what the hell? Use a more efficient counting method with a monotonic stack. Ah, I see. Because what we want to do is just keep track of the smallest. Wait, hold a second. How do you keep... Enumerate each column as the right boundary. Count sub the left and right boundary. I actually have no idea. Let me read again. Convert each row of the matrix into a histogram height. Ooh, each row of the matrix into a histogram height array, where heights j represent the number of consecutive ones extending upwards, with the current row as the bottom. Oh, this? I remember solving some problem like this in the past. I remember. It's the height. For example, if the current row is treated as the base, then height side tells us... Oh, my cat just did something bad, but it's alright. If the current row is treated as the base, then height j tell us how tall the column of ones is at each position. Yes, we can do that. And then we enumerate each column as the right boundary. For each row, once the height is calculated, we use a monotonic stack to find the nearest column on the left for each heights j that has a smaller height. This gives us the left boundary for rectangles ending at j. So we basically, at each row we have a bunch of heights. So at the current one, what I want is to know what is the smallest. And then when you do the smallest, you can compute the distance. So as we go in, okay, we have a height, and then we have a next height. Okay, so if it's a monotonic increasing, so we have a next height. So or we want to make a monotonic decreasing. Suppose the right boundary is at j and the nearest smaller height on the left is I. Then if the left boundary is less than or equal to I, then the subrectangles ending at I have already been counted, extending them to J as no new subrectangle if the left boundary is greater than I. Then it can range from I plus 1 to J, giving J minus I possible positions. Each position can have heights J. So in total, we add J minus I subrectangle. So we are saying that if a smaller one comes in, then I'm gonna pop, right? A smaller height comes in, that every single one that's bigger than me will get popped. And when you pop, everything in between supposedly will be we're using my height as the height. So we'll pop, 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 pop. Eventually I will sit there, right? So when the 0 comes in, yeah, we just pop everybody. Right, when a 0 comes in, we just pop everybody. Let me think again. We got these heights, right? We got a height, we got a low. Low pop the high. Now we got another high. Yeah, what if it just keep going up? I don't know. I think I need to check. So we have heights for each row. Okay. What is this minus 1, 0, minus 1? Okay, I get a current height. If it's larger equal to height. Yeah, if it's larger then we'll pop it. If it's larger than we'll pop it. Larger than we'll pop it until at the end we'll get a top. J is top 0. Previous is top 1. Current is previous plus I minus J. I minus J is the boundary times this height. Because as we pop, because those are bigger than me, so they don't impact, right? So until we hit something that's smaller than me, okay? So this is smaller than me. I still don't know what J is. When you push, right, this is the index. This is the index. So this is the index current. And the height. This is the height. Current is how many I have This is the previous boundary, right? This is the one where it's smaller, right? So we pop everybody in between, so we know that they all have me, so I get this one. But I also include everybody in front. We also include everybody to the left because it's smaller than me, right? So we should include all those. So we added as the current. So we put a current. So we put I, which is the new boundary, right? Which is new boundary. So basically I is the current index. I get its height. I get how many we can get, right? How many we can get ending at this current column with heights not larger than me. Yeah, so everybody. So next, I'm curious, what if a 0 comes in? Because it breaks it, right? It breaks it. So if a 0 comes in, h will just become a 0, right? H will become a 0. And it'll be nothing. So I still get a top. So J will be this. J will be this. So H will be 0. So now I get a 0. But I push 0 in as well. Oh, we push 0 in as well. Yeah, I mean, if H is 0, basically we'll pop everybody. Right, we pop everybody and then we push 0 in. And then the next come in. Yeah, that actually makes sense. I should know. How about the pre? Yeah, the current is 0, but we have a pre. That's not right. Because current height is 0. You should not add pre. So I have something, and now I'm a 0. Right? How can you add pre? Okay, so I push 1. Oh, it's top. I already popped everybody. Now it makes sense. So I popped everybody. So if I am a 0 come in, oh, this one never gets popped. This one never gets popped. So if it's a 0 comes in, it basically will pop everyone. Right, I'll pop everyone. So only this one's left. So when I get this pre, it's guaranteed to be 0. So current is 0. Wow, this is a good solution. Pretty good. But I have no intention to do this one. I mean, I guess if I think hard enough, I may be able to come up with this. Right, the small comes in, I'll collect everybody. And then I will say, yeah, the previous one I probably need to get the index. So I have that. But I think what I will miss is this pre. I think I'll definitely miss the pre. And then I'll figure it out after a wrong test case. And that's an edge case. Another edge case is 0. How do we handle 0? So I'll realize if I want to do 0, then we'll just pop everybody. And if we pop everybody, we just need to make sure the previous is also 0. So that's why we need to have something sitting there. Wow, this is actually very good. Very good one. Okay.